itself. When you're proving an identity, what are you doing? Right, simplify the left, simplify the right, and they should equal each other. Yes? So the types of proofs we've done before have all been very algebraic. Like we've squared this side to simplify it out, which gives you, and I'm going to skip a lot of the work. Oh no, running low on lead. This will give you x to the fourth, and then x squared y squared plus another x squared y squared will give you 2x squared y squared. I'm kind of envisioning my foiling in my head. And then y squared squared will be y to the fourth. So that'll be your left side simplified. Your right side simplified would be when you take 2xy and you square it. That's a monomial, so I can just square each piece. That'll be a 4x squared y squared plus, and when I FOIL out x squared minus y squared, the x squared times x squared will give me an x to the fourth. The outer will give me a minus x squared y squared. The inner will give me another minus x squared y squared, which will be minus 2x squared y squared. And then negative y squared times negative y squared is plus y to the fourth. So they don't match yet, and that's because the right-hand side is not simplified fully. We have some like terms we can combine. We have an x squared y squared term. There's 4 of them. And we have another x squared y squared term. There's negative 2 of them. So 4 minus 2 is 2. So your first term, just so it matches, I'll pull the x to the fourth as my first term. I'll combine the 4 minus the 2 to give me 2x squared y squareds. And then plus y to the fourth. And then both sides are simplified independently of each other, and they equal each other, so I've proven it. Okay? In B, a kind of a different way we've done the identity is it's been phrased where we need to find what certain letters are that would make something an identity. So on this one, we can still simplify the left. Sorry, I kind of ran into it a little bit. If I simplify the left and do 3x minus 4 squared, 3x times 3x is 9x squared. My outer, negative 4 times 3x, will be negative 12x. My inner will also be 3x times negative 4, which is another negative 12x, and negative 12 with a negative 12 is negative 24x. And then negative 4 times negative 4 is plus 16. So my left side is simplified, and really I can't do anything with my right side. But they say, what would A need to be in order for this to be an identity? So we'll answer the question. A has to be 9, B has to be negative 24, and C has to be 16. So a different way of asking about an identity, but a similar concept. Okay? So in Trig, and I say recall, we just did them on the flashcard sheet. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. Cotangent is the reciprocal of tangent. Way back in the beginning, I also told you could write tangent as sine over cosine. I don't know if you remember that or not, but tangent is like when I gave you the first day, I gave you the table. I kind of showed you that it would take a while to do out, so it's not how you're memorizing your tangent values. But if you took the sine of 30 and divided it by the cosine of 30, it will give you the tangent of 30. As tangent is sine divided by cosine. Therefore, cotangent is cosine divided by sine. So that covers 1, 2, 3, 5, and 6. The last and final one is our Pythagorean identity from the other day. Sine squared plus cosine squared is equivalent to 1. And if necessary, we may have to rearrange this. Meaning, if you subtracted cosine squared from both sides, that would leave you with the sine squared of x equaling 1 minus cosine squared x. It's just a rearrangement of that if I subtracted the cosine squared from both sides. If I started over and I actually subtracted the sine squared from both sides, that would leave me with cosine squared x equals 1 minus sine squared. So you need to be able to rearrange that if necessary. And we may come across some examples where that's necessary. Okie doke. And just because we're seeing these reciprocal functions for the first time, I'm also going to take a minute and write if sine equals opposite over hypotenuse, cosecant is hypotenuse over opposite. You follow that? And then if cosine is adjacent over hypotenuse, what's the reciprocal of that, Jack? B. Which function is the reciprocal of cosine? Yeah, but what's the function? It is hypotenuse over adjacent, but what's the function? Correct. And then lastly, if tangent was opposite over adjacent, cotangent is adjacent over opposite. So you will notice, or not notice, I guess, that your calculator does not have these buttons. It doesn't have a cosecant button. So if you are asked to find, for example, the cosecant of 30 degrees, there's no button for that. You have to know that that's the reciprocal of what function? Cosecant Lucas B is the reciprocal of what? Sine. So if I want to find the cosecant of 30, I have to type in 1 over the sine of 30. Now, what mode should I be in? Degree, because it's in degrees. So to find the cosecant of 30, make sure you're in degrees since that's in degrees, and you type in 1 over the sine of 30, which is 2. If I was asked for the secant of pi over 6, what mode should I be in? Radian, so mode, radian. You have to be able to go willingly back and forth depending on the type of problem. So the secant of pi over 6, there's no button for that. So Angie, I'm going to do, what's the reciprocal of secant? Cosine, so I'll do 1 over the cosine of pi over 6. And I get a crazy number, 1.1547. But just so you know, there's no button for these. You have to know the reciprocal functions in order to be able to do them. Good? Okay. So here's where the identity comes back in, and simplifying. We want to simplify the left and simplify the right and pray that they're equal. Okay? One of the first methods you'll look at, and in the simpler problems, this will be all that you need, is to change everything in terms of sines and cosines. Everything. So secant is the reciprocal of what? Cosine. So I'm going to change that into 1 over the cosine of x. Now, cotangent is the reciprocal of tangent, but remember, I want to change everything to sines and cosines. So if tangent was sine over cosine, which is something you should have memorized, tangent is sine over cosine, then cotangent is cosine over sine. Yes? So I'm going to take out the cotangent and replace it with a cosine over a sine. And so when you look now to simplify, if everything is in terms of sines and cosines, there's a better likelihood that things are going to cancel. And what does cancel here? Your cosines. Because you're doing multiplication, so anything in the denominator and anything in the numerator will cancel, and you're left with 1 over sine. Now, on the right-hand side, cosecant is the same as 1 over sine, and then we're pretty much done, right? So you can simplify this all in terms of sines and cosines and get this all in terms of sines and cosines. They should be the same. Or, let's pretend I didn't even want to touch this side. I could, now that that is, kind of crossed itself out and simplified itself a little bit, I could also take that 1 over the sine of x and change it back into cosecant, right? And I could leave my final answer as the cosecant of x equals the cosecant of x, having never touched that. That's an option. Just like in geometry, there's not one and only one way to do a proof. Okay? So I could have stopped the left-hand side here and just changed cosecant to 1 over sine of x. And so my final step there would have been 1 over sine of x equals 1 over sine of x. And I could have been done. Instead, I never touched this at all, and I brought this one back into a cosecant. You have options, okay? Especially towards the end. Any questions there? Okay. Number 2, Jason, what, if anything, are you going to do to the sine of x? Nothing, because it's already a sine. Times the tangent of x. What, if anything, Bella, are you going to do to the tangent of x? Nope. Our first goal should be to get everything in terms of sines and cosines. So I said we want to get everything into sines and cosines, not everything into cotangents. Chris Brooks, help her out. Change it to sine. So there's 2 options when you deal with tangents. Number 1, you can flirt back and forth between tangents and cotangents. Or number 2, you can just do sines and cosines. What? Flirt back and forth? Oh, you kids. So I'm going to make it sine over cosine. And then plus, what can I do with cosine? Leave it. For now. Okay. And then order of operations says we would have to do multiplication first, right? So sine x is technically over what? 1. And so sine x times sine x up top is going to be sine squared over cosine x plus cosine x. Then order of operations would say add these together. But I can't add them together until I have a common denominator. So this right now is a denominator of 1. So what does it need? Cosine x. Which means, what is this numerator going to become? Cosine squared. So now that they both have a denominator of cosine x, I can add their numerators. Sine squared plus cosine squared. All over the common denominator. I forgot to write it. Nothing. Thank you. Normally I would keep going down, but I've shorted myself some space here. What about this can now be simplified? No, you cannot cross out the cosine because this is a piece of a polynomial. That's the first of a gazillion times I'm going to remind you of that. But that's a common mistake. You can't cross out a denominator ever with a piece of a polynomial. I'm more focused on the numerator. Sine squared plus cosine squared equals what? 1. So this side, and again, I would continue to work down, but I have to start moving over. That numerator just becomes 1 over cosine x. And so that's where I'll end my left side, because my right side, which was a secant is the reciprocal of cosine. So I can rewrite secant as 1 over cosine x, and there's my left side equals, there's my right side. Done. Follow? So all things in terms of sines and cosines, and then also you may have to get common denominators and add things together to do your simplifying, to do your operations. Any questions? All right, this one. If you're looking at the left-hand side, it's already in terms of sines and cosines. Anybody see an opportunity to do anything to help simplify this? What'd you say? Not cancel them out, but I like that you notice that both terms have a cosine. What if it was a 5? What if it was 5 minus 5x? Factor. Yes? Take out a GCF. They both have a cosine. So if I pull a cosine x out in front, what's left of this term when I divide off a cosine x? 1 minus what's left of this side, or this term when I divide off a cosine? Just the sine squared. Now, anytime you see sine squareds and cosine squareds, or 1 minus those, you should be thinking about the Pythagorean identity, or one of the many, and I only did a couple of them, rearranged versions of that. In the problem where we are right now, we see a 1 minus sine squared x, right? Isn't that what's left? 1 minus sine squared x. Because of that Pythagorean identity, 1 minus sine squared x can be replaced with cosine squared. Follow? So this piece we replace with cosine squared. So we have cosine x times cosine squared x. And cosine times a cosine squared will become a cosine cubed. And I'm done, because this side is already cosine cubed. Yeah. You can never, when you're proving, do the same thing to both sides. No. That's a solving technique. Do you follow? You remember that rule? So even though you'll do that and you'll see it, like, oh yeah, see, it works out, and you'll know, we don't prove things that way. We have to treat them both entirely individually. Okay? I do want to show you one more thing on this problem. Let's pretend you didn't see the factoring. And like I said, there are options. If you didn't see the factoring, maybe you would see the sine squared. And if you go back up, again, because Pythagorean identities should make you be a little bit conscious anytime you see a sine squared or a cosine squared. So if I see that sine squared, what can I replace sine squared with? I can replace it with 1 minus cosine squared. And let's just see how that unfolds. Sometimes it works, sometimes it doesn't. So cosine of x minus cosine of x, parentheses, and I'm replacing the sine squared with 1 minus cosine squared. And simplifying would tell me on this side I need to do what next? Starts with a D and ends with distribute. Oh my gosh. I'm going to distribute a negative cosine x. So this first cosine x is still there. Negative cosine x times 1 is minus cosine x. And negative cosine x times negative cosine squared, the double negative makes it a plus. The cosine times cosine squared makes it a cosine cubed. And then when you combine like terms, these cancel. Right? Cosine x minus cosine x, gone. Cosine cubed x equals cosine cubed x. So there are multiple ways, and I want you to know that there's no right or wrong way, but I need you to see that factoring is always an option. Substituting out sine squareds or cosine squareds is also always an option. Okie doke? All right, last one. Which side would you like to simplify first? Okay, so who said left? Chris Brooks. What would you do to the left-hand side, Chris? One over cosine. Well, it's a binomial, so both terms have to be divided by cosine. You know how in linears, if you've got like 8x plus 4 and you're dividing it by 2, you have to divide both terms by 2? Do you follow that? So you can do that. If we're doing it Chris's way, this is a binomial divided by a monomial. So both terms have to be divided by cosine. So that would be 1 over cosine x plus sine x over cosine x. And this is, Chris, I think where you were talking about the 1 over cosine is the same as secant. And sine over cosine is the same as tangent. And, as it so happens, we're done. So the point of me putting that one on there is I do want you to realize that if you have a binomial on top or a trinomial on top and you're dividing by a monomial, you can divide each piece individually by that and see if that strikes something up. Okay? I actually, though, based on what I've taught you so far, I do agree with the people that said they would do the right-hand side first. Because the secant, my whole thing started with change everything to sines and cosines. And this side is already sines and cosines, so what can you do with it? But the secant side, you can make 1 over cosine x plus sine x over cosine x. So everything is sines and cosines. And in order to do addition, you need a common denominator. You already have a common denominator. So just add those fractions and treat it as one fraction. And then you never have touched the left-hand side, and you're done. Follow? Either one work. Okay? All right. Now, I'm trying to see anything on the back that you think. This one, I think, will be just changing everything to sines and cosines, and I think it'll all work out when stuff cancels. That's kind of a mimicked version of number 1, just different things. This one is more like the factoring one that Elena pointed out. I could factor out a cosecant. Yes? And eventually I may want to change my cosecant to 1 over sine, but you kind of would see how that would pan out. Maybe this one's tricky. So I'm going to show you kind of 2 options for this one. If you go with my instruction, which is sines and cosines, your tangent will be sine over cosine times your cotangent will be cosine over sine all over, and there's kind of the danger in that is that now we've created fractions within a bigger fraction. Do you see that? Because on my denominator, my cosecant would be 1 over sine. But within that numerator, what's nice about this is sine of x and sine of x cancel. Cosine of x and cosine of x cancel. So what's in the overall numerator? 1. So it's 1 over the sine of x. And when you have a number divided by a fraction, you keep the 1, you change the division to multiplication, and you flip the 1 over sine x to sine x over 1. And so what is all that? What's 1 times sine x over 1? Sine x. And your right-hand side was sine x. So that would be done. Okay, so a little bit of the possibility of complex fractions. The other thing I was thinking on this one was, rather than doing sines and cosines, if I realize this, tan of x times the cotangent of x, and cotangent is 1 over tangent. See how that would just become 1 anyway? Anytime you multiply something by its own reciprocal function, it's just 1. So like sine times cosecant would just be 1. But you probably still want to show that out, so it would be 1 over cosecant, and cosecant is the 1 over sine, and 1 over the 1 over sine becomes sine. It's like the reciprocal of sine, which puts you back to just sine. Okie doke? Oh boy. Cosecant squared. I'm just going to do this so I can work down. Cosecant squared, cosecant is the reciprocal of what? Sine. So cosecant squared is the same as 1 over sine squared. All over. Cotangent is what over what? 1 over tan, but let's pretend I was getting all sines and cosines. No, sine over cos is tangent. So cotangent would be cos over sine. Follow? If tangent is sine over cosine, cotangent is cosine over sine. And how do you take a fraction and divide by a fraction? Keep, change, flip. So keep, change, and flip cosine over sine, now 2 sine over cosine. What cancels? Not fully, but this sine fully cancels with one of the two of those, right? Leaving just a plain sine x on the denominator. So it's 1 over sine x times cosine x. So I don't know if you want to do anything with that, or if you're happy with how that's simplified, and then we could work on the other side. So we simplified the left maybe as far as we can see. What would you do to cosecant? 1 over sine times, what would you do with secant on the right? 1 over cosine. And when you're multiplying fractions, do you need a common denominator? No, you just multiply across. So up top, 1 times 1 is 1. And on the bottom, sine times cosine is sine times cosine. You're done. Good? So this is the last skill. Anything after the midterm is great, yeah? So, with proving identities, there is no solution, right? It's not like x equals 5 and you check whether or not you got it right, okay? Not only that, there's multiple solutions. It's like trying to look at a solution for a proof in geometry. It's not just one answer, am I right or am I wrong? There's like the process is your answer. So it's going to be kind of tough for me to give you answers on this. Not only that, there are multiple ways you've seen. I've shown you 2 ways to do the same problem. So instead of giving you the solutions, because I really can't, I'm just going to really give you the answer. Something to use as a guide to, like, if you get stuck, like, how could I do this? So try it on your own, and then if you feel like it worked out, it probably did, as long as you didn't, like, make up some math rule along the way. If you feel like it worked out, it probably did. You may look at my answer sheet and see it's the exact same way I did it, or you may look at my answer sheet and see that I did it a totally different way, but they both might be valid. So your questions tomorrow might more be like, I think I did this one right, but it's different than yours. Can you check it and see if this would also work? Does that make sense? Take. Enjoy. Lucas, Kay, did you get homework? Lucas. Lucas. Those headphones I saw there. Perhaps he doesn't want solutions.